Hi everyone and welcome to week 6 of Introduction to Logic. This week we're going to be continuing adding to our system of natural deduction rules and looking at rules of replacement. Rules of replacement are sometimes called rules of equivalence, and I think you'll see why as we dive in and look at the rules. So we're going to dive right in. Let's look at the first rule. I've actually rearranged these from the order that they're presented in the textbook. I'm presenting them here in order from easiest to understand to hardest to understand. So let's dive in and look at the first rule, the easiest to understand of the equivalence rules. So first of all, right off the bat, you're introduced to a new symbol. Right here, what looks like two colons right next to each other is a symbol that's used to mean equivalence. What it says is that what's on the left is logically equivalent to what's on the right. In fact, if you construct a truth table for this, you'll see that P is equivalent to not P, or two tildes in front of a P. And of all the equivalence rules, this is the rule that's easiest to understand. Obviously, a double negation cancels itself out, right? If P is true, then not P would be false, and not P would be true again. So whatever you plug in for P, whether it's simple or whether it's complex, P is always going to be equivalent to not P. What this means is that in the context of a proof, whenever you encounter a double negation, you can eliminate that double negation and just have the statement that has the double negation in front of it on its own line. Likewise, you can actually go the other way around. You can always introduce a double negation anywhere you want inside the context of a proof, even in the middle of the line. And right off the bat, this is the thing that distinguishes the equivalence rules from the implication rules that we looked at over the last couple of weeks. The implication rules, what the textbook calls rules of implication from Hurley section 7.1 and 7.2, those rules can only be applied to an entire line, to the main operators of the statements in the context of a proof. Equivalence rules, or rules of replacement, allow you to apply the rule even inside a larger statement. And we'll see what this looks like when we dive in and start looking at proofs. Right now, I just want you to focus on the forms of the rules themselves. So this is a pretty easy to understand rule. Obviously, P is equivalent to not P, and vice versa. Whenever you have not P, that's equivalent to P. So you can add or remove a double negation whenever you encounter one in the course of a proof. Let's move on. The next easiest rule to understand is what's called commutativity. It's abbreviated COM. The way this rule works, and again, this is a pretty obvious rule. Some symbols are reversible. So for example, if you have P or Q over here on the left, that's equivalent to Q or P. And you could do a truth table for this and show that these two statements are equivalent, but you really don't need to. If you just talk through the meaning of these operators, you'll see why. P or Q over here on the left, that's going to be true if one of the two disjuncts, P or Q, is true. And obviously, the same conditions hold up for the statement on the right. Q or P is going to be true if at least one of the two disjuncts, Q or P, is true. So they have the exact same truth conditions. So those two statements are logically equivalent. What this means is that you can reverse the order of any disjunction you find in the context of a proof and rewrite a statement with the disjunction reversed on its own line. The same is true of conjunctions. P and Q is equivalent to Q and P. And I think this is equally easy to see why this is the case. P and Q over here on the left is true if both P and Q are true, and it's false otherwise. Likewise, Q and P is going to be true if Q is true and P is true, if both of the two conjuncts are true. And it's going to be false otherwise. So again, these two expressions have the same truth conditions. They're logically equivalent to each other. This means that in the context of a proof, you can reverse the order of a conjunction or reverse the order of a disjunction anytime you encounter one and rewrite the statement with that disjunction or conjunction reversed on its own line. Now, here you have to be really careful. P implies Q is not the same thing as Q implies P. So be really careful. This rule does not apply to the horseshoe operator. Okay, so commutativity is pretty easy to understand. We'll see how this applies in the context of a proof in just a few minutes. The next rule that I want to talk about is De Morgan's rule. This rule is getting a little more complex, a little harder to recognize. I still put this in the category of fairly easy rules to recognize and fairly easy rules to use, but let's talk through the reasoning. If you have a statement like this, the negation of P and Q, that says it's not the case that P and Q are both true. Well, there's only one way for P and Q not to be true at the same time. Either P has to be false or Q has to be false. So a statement like not both P and Q is equivalent to not P or not Q. Either P has to be false or Q has to be false. And again, you can memorize these rules structurally, but I really want you to take the time to talk through the reasoning of these rules and internalize why they work. This rule also applies to a statement like this. If you have the negation of P or Q, that says neither P nor Q is true. It's not the case that either P is true or Q is true. This says that P has to be false and Q has to be false. One way people sometimes think about De Morgan's rule is if you're kind of distributing this negation to both terms and changing the sign of the operator from a conjunction to a disjunction or from a disjunction to a conjunction. I'm not wild about that way of thinking about this rule because it's easy to confuse this rule with another rule called distribution that actually is called distribution. So if this rule of thumb kind of helps you mechanically see how to apply De Morgan's rule, that's great. I don't want you to confuse this rule with distribution though. But you can see mechanically that's what's going on here. This tilde has kind of been applied to both of the two conjuncts, and the conjunction operator has been changed to a disjunction. So that's one way you can think about De Morgan's rule. And it works the other way as well. This tilde here has been applied to both terms, and the operator sign has changed from a disjunction to a conjunction. That's a very mechanical way of thinking about De Morgan's rule. But most importantly, I want to make sure you take the time to think through the reasoning and why it works. If it's not the case that P and Q are both true right here, then either P has to be false or Q has to be false. And if it's not the case that either P or Q is true, that means neither P nor Q is true, which means P is false and Q is false. Very easy to understand rule if you take the time to think through the reasoning. The next rule I want to look at is called associativity, what's abbreviated ASSOC, sometimes just Assoc. The rule works like this. If you have a string of disjunctions, P or, and then another disjunction in parentheses, Q or R, you can shift these parentheses around. You can convert that statement to P or Q in parentheses or R, as if you had moved the parentheses over a bit. And the reason this works is that if you look at this first statement on the left, P or Q or R, in order for that statement to be true, one of the two disjuncts has to be true. P would have to be true, or this expression in parentheses would have to be true. But in order for that expression in parentheses to be true, either Q has to be true or R would have to be true. In other words, in order for this statement to be true, at least one of those three disjuncts, P or Q or R, would have to be true. And the same conditions hold if you shift the parentheses around. In order for P or Q or R to be true, either R would have to be true or P or Q would have to be true, which means that either P or Q or R would have to be true. So they have the exact same truth conditions. And you could test this on a truth table on your own if you like. I'm not going to take the time to do that now. This also works for conjunctions. If you have a statement right here like P and Q and R, what makes that statement true? Well, P has to be true and Q and R has to be true. But in order for Q and R to be true, Q has to be true and R has to be true and P has to be true. All three of those statements, P, Q, and R, would have to be true. And the same over here if you shift those parentheses around. If you have P and Q and R, P and Q would have to be true, which means P has to be true, Q has to be true, and R has to be true, and the exact same truth conditions hold. So this is a fairly easy rule to apply. Basically means you can shift the parentheses around if you have a string of disjunctions or a string of conjunctions. The last new rule is called distribution. And this rule basically works like this. This one, of all the rules that you're going to learn, the rules of equivalence or rules of replacement, this is probably the hardest rule to learn to apply correctly and the hardest to recognize. So make sure you spend a little bit of extra time in your homework exercises with this rule when you encounter it in the context of the proofs you have to do for your homework. So distribution basically works like this. If you have a statement like P and Q or R, now one distinguishing characteristic here to look out for is that these are not the same operators. These are either conjunctions or disjunctions, not both conjunctions or not both disjunctions. And if you look back at associativity, here you have the same operator, both conjunctions right here, or disjunctions up here, both conjunctions right here. But for distribution, you actually have the opposite operators, disjunction or conjunction. The reason that this is called distribution is that you're essentially distributing this term P to both of the terms here inside the parentheses. So for example, P and Q or R is equivalent to P and Q or P and R. And it works the other way around. If you have the disjunction outside the parentheses and the conjunction inside the parentheses, P or Q and R is going to be equivalent to P or Q and P or R. So it's as if you're distributing that outside term to both of the terms that are inside the parentheses. Again, this can be a very tricky rule to recognize because it works in reverse. Whenever you have statements on the right as well, you can use distribution and make them look like the statements on the left. So this is a little tricky to recognize in the context of a proof. Look at the sample exercises that you're given inside your textbook chapter. Look at the correct answers in the back of your textbook, and look at the examples I'm going to do in this video here when we encounter distribution. Get lots of practice recognizing this. Of all the rules that you're going to encounter this week, this is probably the hardest to recognize. Okay, let's go ahead and dive in and do some proofs using these new rules. Now, again, like all of the new rules you're going to learn, these rules are in addition to the rules that you've learned previously. So up till now, you've had 8 implication rules, and you have a new batch of replacement rules, or what's called equivalence rules. And you can use any of the rules you've learned up till now to do all the proofs for this week. And that's going to be true for the subsequent weeks as well. Okay, so in this proof, you're given 2 premises. Not P implies M, and not N implies Q. Number 2, the second premise is it's not the case that M and N, negation of M and N, and we're trying to show P or Q. So like all proofs, when we get P or Q on its own line, we are done with this proof, and we'll have shown that this conclusion follows from those premises. Now, I just want to make a little start here. This is actually an exercise from your homework. So this is kind of a freebie for those who are taking the time to watch the videos. But I do want you to follow through and see how these rules are applied strategically to get from what you're given in the premises to the conclusion that you're trying to show follows. So we're going to add a new line, line 3. The first thing I notice, well, there are a few things. I could just dive in, but I want to talk about a few things that I notice. I notice that line 2 right here kind of looks like De Morgan's rule. It's the negation of a conjunction. We could use De Morgan's rule on that. The other thing I notice is that the conclusion is a disjunction. We have P or Q, and those 2 terms appear right here in premise 1 as the consequence of the 2 conditionals that are conjoined together with that dot. So this is starting to look like a constructive dilemma. So even from a cursory look at this proof, I'm guessing that I'm probably going to do a De Morgan's rule step, and I'm probably going to do a constructive dilemma step in the context of this proof. That's just a guess. I don't know until we've actually done it. But from looking at the proof as it's given, that's what I think we're probably going to end up doing. Let's do that first De Morgan's rule step. We said that when we have the negation of a conjunction, again, I want you to make sure you understand what you're doing here. This says it's not the case that M and N are both true. In order for that to be the case, you know that M has to be false, not M, or N would have to be false. Either one would have to be false. And this is what De Morgan's rule tells us. So this comes from line 2 by De Morgan's rule. In fact, let me use a different color here for clarity. Line 2 by De Morgan's rule. Okay. As predicted, this is really starting to look like a constructive dilemma now. This is one of the rules you learned originally. So we have 2 conditionals that are conjoined together. Not M implies P up in line 1, and not N implies Q in line 1. We know that one of those 2 antecedents, not M or not N is the case. That's what line 3 tells us. So we know that one of those 2 consequences, P or Q, would have to be true. And that's what constructive dilemma tells us. So P or Q. And this would follow now from line 1 and 3 by constructive dilemma, CD. And we're done. We've got the conclusion on its own line, so we've shown that this is a valid argument. So you can see here that some of these rules are applied strategically. We used De Morgan's rule here so we could set up this constructive dilemma step on line 4. And a lot of these equivalence rules are like that. You'll apply them strategically so you can do a subsequent step that you happen to recognize that you'll need to do. And again, that just takes practice and insight, pattern recognition, to be able to recognize that in order to do a certain step that you know you need to do, you have to do some preliminary step so the subsequent step matches the form of the rule that you recognize you're going to need. Okay, let's keep going. This is a very interesting argument. We have just one premise, not S, and we're trying to show this conclusion, the negation of F and S. And I think you can see why this follows. If not S is the case, then it can't be the case that F and S are both true because S isn't true. So obviously that conclusion follows even though the letter F is not in the premises. One helpful thing you can do with equivalence rules is work backwards. So one thing I'm going to do here at the very bottom right of the screen, in fact, I'll do it on the bottom left. If the conclusion we're trying to get is the negation of F and S, by De Morgan's rule, we could work backwards and know that in order to get that, we're going to need to get not F or not S, right? These two statements are equivalent by De Morgan's rule. Well, how can I get not F or not S? I already have not S. So I'm going to add a new line right here, line 2. And I'm going to use addition, which again allows you to take any statement you have previously in a proof using a wedge and disjoin any term you want, even a letter that's not already in the proof, onto a statement you already have using the wedge. So if we have not S, I'm going to add not S or not F. I'm going to add not F on using a wedge by addition. So this follows from line 1 by addition. And this is starting to look a lot like what we need, right? We have not S or not F. We just need not F or not S. Remember, you've only finished the proof when you have the conclusion that matches exactly on its own line. It has to be exactly the same. It can't be similar. It can't just be the same terms in a different order. It has to be the exact same conclusion. So how do we get there? Well, if we have not S or not F, we can just reverse the order of that disjunction using the commutativity rule, one of the new rules that we have for this week. That's going to be equivalent to not F or not S. So that would follow from line 2 by commutativity, C-O-M. I'm going to do just a little bit of cleanup here. Whenever you work backwards like this, sometimes this is scratch work. And you'll go, okay, now I know exactly what I need to do to complete this proof. So I'm going to erase all this scratch work and complete the proof. We said that this statement, not F or not S, was equivalent to the conclusion by De Morgan's rule. So we get not F, the negation of F and S, like so. And that's going to follow from line 3 by De Morgan's rule, DM. And again, I think you can see why, right? 3 says either not F is the case or S is the case. It means one of those two terms, F or S, would have to be false. And obviously, if one of them is false, it can't be the case that both of them are true. Therefore, number 4 follows. It's not the case that F and S are both true. That's what De Morgan rule says. Okay, fairly simple proof. But when you first encounter this, you might really wonder where the heck this letter F comes from that's not given in the premises. And you can see here that the way we introduced that letter F was according to the addition rule. Okay, for our next proof, we have two premises, the negation of N and T. 2 tells us that T is true, and we're trying to show not N. That's the conclusion. Well, let's dive in. This one's actually fairly straightforward. On line 1 looks a lot like a De Morgan's rule step. We have the negation of a conjunction. So from De Morgan's rule, we know that not N or not T. That's going to follow from line 1 by De Morgan's rule, DM. Again, De Morgan's rule is a fairly friendly rule. When you first start to encounter it, it'll take a little practice to get it right, but this is one of the easier rules to recognize and to apply correctly. Just make sure you change that operator from a conjunction to a disjunction or from a disjunction to a conjunction. Okay, looking at the proof now, line 3 says that either N is false or T is false, right? Not N or not T. But in line 2, we know that T is true. So we really have the opposite of one of these terms. We have not T here on line 3, but we have T on line 2. So this is starting to look a lot like a disjunctive syllogism, but we need to make it match the form of a disjunctive syllogism first. So remember, for a disjunctive syllogism, the term that you have the negation of has to be on the left. So we need to get this not T and put it on the left side of that disjunction. So we can use the commutativity rule to rewrite line 3 as not T or not N. Just reversing the order of that disjunction. So that's going to follow from line 3 by commutativity, C-O-M. Okay, now we're really getting close to a disjunctive syllogism step. On line 4, we have not T or not N. Line 2 tells us that T is true. But remember, in order to use disjunctive syllogism, you have to have the negation of this term on the left, not just its opposite, but its literal negation. So in order to use disjunctive syllogism, you need to have not T. We have T, but we don't yet have not T. But we do have the double negation rule that lets us introduce a double negation anywhere inside the proof. Here we need not T, and we have T, so we can introduce a double negation, not T. And this is going to follow from line 2 by double negation, dn. And I want to make sure you really see why I'm doing this, right? On line 4, we have a disjunction. Either T is false or N is false. Well, we know T is true, but we need to take T and make it the negation of not T, not T. That's why we use this double negation step. So this might be a little tricky when you first encounter it, when you know you need to not just remove a double negation, but actually introduce a double negation in order to be able to do a subsequent step of the proof. Okay, now we're almost done. Line 4 says not T or not N. Line 5 says not T. So we know the term on the left is false. So the term on the right, not N, would have to be the case. Not N. And that's going to follow now from line 4 and line 5 by disjunctive syllogism, DS. So really, there were just a couple of key steps here. You had to recognize this De Morgan's rule step right off the bat, but you also had to use a couple of these little equivalence rules to set up this final disjunctive syllogism step that we applied in line 6. So, and again, equivalence rules and rules of replacement are often like that. You'll apply seemingly obvious little steps so you can apply a more important step later in the proof. Okay, next proof. Here we're given 3 premises. R implies not B. Line 2 says D or R. 3 says B is the case, and we're just trying to show that D follows. I think this is going to be a fairly straightforward proof. So line 1 says, if R, then not B. And we know B is actually true, which is the opposite of not B. But in order to do modus tollens, I think you can see this is starting to look like a modus tollens step. We have R implies not B. We have the opposite of the consequent, but we need the negation of the consequent. If the consequent here is not B, in order to use modus tollens, we need not B. So we're going to introduce a double negation here. We're going to say from line 3, B, we're going to get not B. And that's going to follow from line 3 by double negation. So we're introducing this double negation for the sake of being able to do a modus tollens step together with line 1. This should all be review. Line 1 is a conditional. If R, then not B. We have the negation of the consequent now, not B. From that, we know we can get not R, the negation of the antecedent. And again, if that step is confusing, go back in a couple of videos and watch the video where modus tollens is introduced. Hopefully this is review at this point. So this follows from line 1 and line 4 by modus tollens, MT. Okay. So line 2 tells us that D is true or R is true. And we know R is false according to line 5. So from those, we know that D has to be true, which is the conclusion we're trying to show. But in order to use disjunctive syllogism, the term that you have the negation of has to be on the left. Here we have D or R. We know R is false. So in order to use disjunctive syllogism, that R has to be on the left-hand side. So we're going to use commutativity to reverse the order of the disjunction in line 2, R or D. And that's going to follow from line 2 by commutativity. And we're doing that step so we can do the next step, which is a disjunctive syllogism step. But again, I'm going to go really slowly here. Line 6 says R or D, either R is true or D is true. 5 tells us that R is false. So from those 2 statements, we know that D has to be true by disjunctive syllogism, one of the rules that should be reviewed at this point. 5 and 6 by DS. And we're done. We've shown that D follows from those premises. So again here, what's like empowering but also a little frustrating is you might see that you might need to do a disjunctive syllogism step, but in order to use that rule correctly, you've got to do this little intermediary step, this commutativity step. And you might see that you can do modus tollens right here, but in order to do that, you needed to first use this double negation step, so the statements you have match the form of the rules as they're defined in this textbook. There's no way around that. This is how proofs are done correctly. So get lots of practice doing this. And if you skip these little steps, even if they're seemingly obvious, if you should have applied a double negation step or a commutativity step somewhere, I will ding you on your homework assignment. So make sure you pay attention to how I'm setting up these more important steps. Like here, the really important steps of this proof are this modus tollens and this disjunctive syllogism. The double negation is kind of a setup step so you can do modus tollens. The commutativity step is a setup step so you can apply that disjunctive syllogism. But I will ding you if you miss those steps, if you misapply the rules incorrectly to statements that don't match the form of the rule yet. Okay, moving on. Here we're given two premises. If O or M, then S. Line 2 says S is false, and we're just trying to get not M on its own line. Okay, let's dive in. I think there's one really obvious starting step here. Line 1 is a conditional. It says if O, then M. Excuse me, if O or M, then S. Line 2 says S is false, so we have the negation of the consequent. From modus tollens, we know we can get the negation of the antecedent then, so it's not the case. And here everything in parentheses, O or M. And this is going to follow from lines 1 and 2 by modus tollens. I think that's a pretty obvious first step in this proof. The next thing I see is that line 3 looks like one of the forms for De Morgan's rule. We have the negation of a disjunction. And again, I'm going to talk through this reasoning just to make De Morgan's rule a little more intuitive for you. Line 3 says it's not the case that either O or M is the case. It's not the case that O or M is true. Well, if it's not the case that either one is true, O has to be false and M has to be false, not O and not M. And that's going to follow from line 3 by De Morgan's rule. So you can see I've taken this negation, I've moved it in front of both terms that make up this disjunction, and I've changed the operator from a disjunction to a conjunction. But really, that's a very mechanical way of thinking about it. I want you to have this richer, more semantic understanding of why De Morgan's rule works. Okay. Well, line 4 says not O and not M, and that says not O is the case and not M is the case. And we're almost there. We're trying to show that not M is the case. We need to get not M on its own line now. 2 steps are going to be necessary to do that. I think you can see that line 4 is a conjunction. 2 things are the case, not O and not M. And if both of those are the case, obviously one of them would have to be true. Not M would have to be true. But in order to use simplification, not M has to be on the left side of that conjunction. So we need to rewrite this conjunction, switching the order of the 2 conjuncts. So from line 4, I'm going to do just a little cleanup here. There we go. From line 4, we're going to get not M and not O. The same conjunction in line 4, but reversed. And that's going to follow from line 4. Trying to change colors here. Line 4 by commutativity, C-O-M. And now we can simplify and get that term on the left side of the conjunction in line 5 on its own line, not M. From line 5 by simplification. So again here, you had to do a fairly obvious but important nonetheless step on line 5, rewriting the order of that conjunction, switching around the order of the 2 conjuncts so you can use simplification, which only applies to the term on the left side of a conjunction. And this is some of the practice of doing proofs that you'll need to get. You'll need to practice recognizing the intermediate setup steps you'll have to do to be able to apply the major rules that let you force a proof forward. Okay, next proof. We're given 2 premises, K and H or K and L. We know L is false, and we're trying to get H. So the first thing I notice is that line 1 looks a lot like one of the forms for distribution. We have K and H, or we have K and L. And according to the distribution rule, that's going to give you K and H or L. Right, according to distribution, if you applied distribution in line 3, that would give you K and H or K and L, which is what we have in line 1. So this is going to follow from line 1 by distribution. And it might take a little practice to recognize that first step. Let's move forward. Well, we could simplify and get k on its own line. And really, whenever you see a conjunction, I would go ahead and do this step. So I'm going to simplify line 3 and get k on its own line. Now, it turns out I'm not actually going to need this step, but it's such an obvious step, I usually do it anyway whenever I encounter it, even if I end up having an extra step in the proof. I really don't mind if you have an extra step in your proof. What I do need is this H or L, and I think you can see why. If you can get H or L on its own line, we know L is false, which means H would have to be true, and that's the conclusion. But we need H or L on its own line first. How am I going to get there? Well, I can use simplification, but H or L has to be on the left side of that conjunction. So I'm going to rewrite line 3, switching around the order of the conjunction. We have H or L and K. So that's going to follow from line 3 by commutativity. And now I can simplify and get H or L on its own line. And that's going to follow from line 5 now by simplification. So again, here's a really obvious case where you have to apply an intermediate step, this commutativity step on line 3, so you can apply simplification the correct way. And if you skip that step, I would ding you on your homework exercises. So make sure you don't miss those intermediate steps. We're almost there. We have H or L. We know L is false on line 2. This is starting to look like a disjunctive syllogism, but in order to use that rule, the term of the disjunction that you have the negation of has to be on the left. So in order to use disjunctive syllogism, we have not L, we would need L to be on the left, L or H. So I'm going to use commutativity to switch around the order of the disjunction on line 6, L or H. So I can use disjunctive syllogism correctly. That's going to follow now from line 6 by commutativity. Same thing, in fact, I'll circle it in green here. I'm doing commutativity so I can set up the subsequent step. Okay, we're almost done. On line 7, we have L or H. We have not L. From disjunctive syllogism, then, we know that H has to be the case. And that's going to follow from line 2 and line 7 by disjunctive syllogism, DS. And we're done with that proof. We've shown that the conclusion follows. Okay, that one wasn't too bad. Next proof. Line 1 tells us that we have H and C and T. Line 2 tells us it's not the case that not F and T, and we're trying to show that F follows. So there are a couple obvious starting points. I'm going to dive in and try something, and this is one of these things where, you know, when you try something in a proof, maybe it will work, maybe that will be conducive towards reaching the conclusion. Maybe it will be a wrong path. You know, maybe you'll have to back up and try something else or keep going and try a different strategy. What I noticed right off the bat, line 2 looks a lot like De Morgan's rule. It's the negation of a conjunction. So by De Morgan's rule, I would get not F or not T. And that would follow now from line 2 by De Morgan's rule. Make sure you don't lose track of these negations, right? In order to use De Morgan's rule, you take this negation outside the parentheses, apply it to both terms, and then switch the operator from a conjunction to a disjunction. So make sure you don't lose track of these negations. We're going to get not F or not T. Now, obviously, not F is equivalent to F. So we're going to use double negation to get rid of that double negation on line 3. So I'm going to rewrite line 3 as F or not T. And that's going to follow from line 3 by double negation. Now I want to pause here for just a moment and show you what I did. I applied double negation, but I only applied it to a part of the statement. I just applied it right here, and I left the rest of the statement alone. I didn't change anything right here. And this is something that's true about equivalence rules, or what the textbook calls replacement rules in general. You can apply them not just to the main operator, but anywhere in any other statement that you find an instance of that form, you can apply the equivalence rule or the replacement rule inside of a larger statement. And that's what I've done here. I've applied double negation just to that little part of line 3. And that is what distinguishes rules of replacement from the rules you've learned up till now, the rules of implication. Okay. So what I see next is that I'm trying to get F on its own line, and I have a disjunction with F in it on line 4, F or not T. So if I could get the opposite or the negation of this other term, not T, then I could get F pretty easily by disjunctive syllogism. I just need to switch around the order of the disjunction using a commutativity step. So how can I get not T? Well, not T is just T, which I have up here on line 1. I just need to break apart this string of conjunctions on line 1 to get T on its own line. The rest will fall out pretty easily if I can manage to do that. So we have a string of conjunctions here. There's a few ways I could do this. I'm going to do it using the rule associativity that you've learned up till now. So by associativity, whenever you have a string of conjunctions, you can shift around the order of the parentheses. So I can rewrite line 1, putting the parentheses around H and C and T. That would follow from line 1 by associativity, ASSOC. Okay. Now, this is helpful because we have T over here on its own, but we can't use simplification yet because T isn't on the left side of that conjunction. So I'm going to rewrite line 5 now, switching around the order of that conjunction that's the main operator. I'm going to get T and H and C in parentheses. And that's going to follow from line 5 by commutativity, COM. Now I've got T on the left side of that conjunction on line 6, and I can simplify it to get T on its own line. Just T. And that's going to follow from line 6 by simplification. And again, the nice thing about doing this class by video is that if you need to pause and see why I've done a certain step, pause the video, make sure you can understand why I'm doing each one of these steps. If it's obvious, just blaze forward with me. But if you need to pause and reflect and see exactly how I got any given step or why I'm applying any given step, pause and make sure you understand why I'm doing every step. Okay, now I've got T on its own line, but we said a moment ago that we need not T. We need the negation of not T, which is way up here in line 4. So I'm going to do double negation on line 7 to get not T on line 8. And that's going to follow from line 7 by double negation, DN. And I'm doing that so I have the negation of one of these disjuncts way up here on line 4. Okay. But in order to use disjunctive syllogism, that term that I have the negation of, not T, has to be on the left side of the disjunct. So from line 4, I need to rewrite this, switching around the order of that disjunction, not T or F. And that's going to follow from line 4 by commutativity. That's what lets you switch around the order of a disjunction. Now I've got a disjunction on line 9, not T or F. I've got the negation of that term on the left, not T. So from line 8 and 9, I can get F on its own line by disjunctive syllogism. So 8, 9, DS, disjunctive syllogism. And you can see, in fact, I'll circle them here. You can see all the intermediate steps I had to do in order to be able to apply, the main rules. The rules that really drive this proof forward are this simplification step and this disjunctive syllogism step on line 10. But in order to do those, I had to do a double negation here, commutativity, another double negation. So a lot of these rules are merely structural. I think you can kind of intuitively see which are the major rules you'll need to do in order to reach that conclusion. But in order to use them correctly, they have to match the form of the rules as they're defined in the textbook. Hence some of the intermediate steps like double negation and commutativity, what I would classify as fairly obvious steps, but are still necessary in order to be able to use subsequent steps correctly. Okay, next proof. We have 3 premises. It's not the case that J or K. Line 2 says B implies K. Line 3 says S implies B. And the conclusion is not S and not J. Okay, let's dive in. I think there are 2 really obvious starting points here. In fact, I'll describe them both and I'll choose one to do. Line 1 says it's not the case that J or K. So we have the negation of a disjunction, and that looks like De Morgan's rule. So I could do De Morgan's rule on line 1 as a starting point. But on line 2 and 3, we see that S implies B on line 3, but B in turn implies K, and that looks a lot like a hypothetical syllogism step. In fact, since that's the obvious rule, one that's review, I'm going to do that one first and see if it's going to be helpful. So from lines 2 and 3, I get S implies K, and that's going to follow from lines 2 and 3 by hypothetical syllogism. Hopefully that's review at this point. Now I'm going to go ahead and do that De Morgan's rule step on line 1. So if we have the negation of a disjunction, it's not the case that J or K, that's going to be equivalent to not J and not K. And that's going to follow from line 1 by De Morgan's rule. Right, I've taken this negation, applied it to both terms, and changed that operator from a disjunction to a conjunction. Okay? Well, let's see. It's always good to look back at the conclusion and see what you need here. We need not S and not J. Well, we have not J on line 5. We just need to get that on its own line, and we're halfway done. So let's do simplification on line 5, not J, and we'll be halfway done with this proof. So line 5 by simplification. In fact, like I said a moment ago, whenever you have a conjunction, it's a good idea to get both terms on its own line. So in order to get not K on its own line, I then have to do a commutativity step, so it's on the left side of that conjunction. So I'm going to rewrite line 5 as not K and not J. Okay, that comes from line 5 by commutativity, COM. And I'm doing that so I can then simplify and get not K on its own line, which I'm going to do right now, not K. That's going to follow now from line 7 by simplification. Okay. So let's see, we've got not J, that's half of what we need. We need not S now, and we're now in a position to get not S on its own line. Line 4 tells us that S implies K, but in line 8, we know that the consequent K is false, not K. So from modus tollens, again, which is a review step at this point, you know you're going to get the negation of the antecedent, or not S, on its own line. And that's going to follow from line 4 and line 8 by modus tollens. Now we're almost done. The conclusion is not S and not J. We have not S. We have not J. So those are on line 9 and line 6. We can conjoin them together and get the conclusion. So I'm going to draw a dividing line here. Line 10 is going to be the conclusion, not S and not J. And that's going to follow now from line 6 and line 9 by conjunction, C-O-N-J. And we're done. We've shown that that conclusion follows. Okay, next proof. We're given two premises, Q or N, or N and T. We have Q or C implies not N, and we're trying to get T. Now, this is going to be a little tricky to recognize. In fact, I'm going to star this. Line 1 looks a lot like the form for distribution, but we have to do a little mechanical switching around in order for it to match the form for distribution exactly. So what I'm going to do commutativity on part of line 1 so it better matches the form for distribution. I'm going to apply commutativity right here. I'm going to rewrite line 1 as N and Q, or N and T. And this is line 1 distribution. Oh, excuse me, not distribution. Commutativity. COM. All I've done is reverse the order of this conjunction here in the first part of line 1. And again, this is another instance of how you can apply replacement rules or equivalence rules to a part of an entire line. Now line 3 matches the form for one of the forms for distribution. I know I can get N and Q or T. Right, if you have a statement like N and Q or T, that's equivalent to N and Q or N and T, which we have on line 3. So this would follow from line 3 by distribution. That step might be a little tricky to recognize. And this is the frustrating thing about doing proofs, is that sometimes there will be a step that you need to do that you just don't see that you need to do, that you need to try some things first, see what you can do using the rules you have, and hopefully you'll recognize a pattern that will drive the proof forward. But there's nothing in the proof that tells you what you absolutely have to do next in order to reach the conclusion. So now we have a conjunction on line 4, in, and, q, or t. I'm going to simplify both of those terms. So right off the bat, I can get in on its own line. That's going to follow from line 4 by simplification. But I'm also going to reverse the order of that conjunction so I can do simplification and get that q or t on its own line as well. But first I need to do commutativity to get q or t on the left. So q or t and in. Just rewriting the order of that conjunction on line 4. That's going to follow from line 4 by commutativity. Okay, and then I'm going to do simplification to get q or t, the left-hand conjunct, on its own line from line 6 by simplification. Okay, let's see what we can do next. The next thing I notice is that line 2 is a conditional. It says if q or c, then not in. Well, we know in is true, which is the opposite of that consequent on line 2, but we need the negation of it. So we need not in order to be able to do modus tollens with line 2. So from line 5, I'm going to introduce a double negation, not in. And that's going to follow from line 5 by double negation, or dn. Now I can do modus tollens together with line 2, and that will give me the negation of the antecedent. It's not the case that q or c. Okay, and that's going to follow from line 2 and 8 by modus tollens. Well, number 9 looks a lot like a De Morgan's rule step. So we have the negation of a disjunction, which says it's not the case that either q or c. Well, if neither one is true, we know that both q and c have to be false. So not q and not c. And that's going to follow from line 9 by De Morgan's rule, dm. Okay. So we're trying to get t on its own line. Don't lose sight of the conclusion here. And on line 7, we know that either q or t has to be true. And line 10 tells us that q is false and c is false. So if we can simplify number 10 to get not q on its own line, we should be able to get t here together with line 7. So let's do that. Let's simplify line 10 to get not q on its own line. That's going to follow from line 10 by simplification. And we said we were doing that so we could do disjunctive syllogism here with line 7. Right? Line 7 says q or t. 11 tells us that q is false, so we know that t has to be true. And that's our conclusion, which is going to follow now from line 7 and line 10 by disjunctive syllogism, and we're done. Okay, so this is a pretty tricky proof, but the only reason that I think you can see most of it came together pretty quickly. The only thing that makes this proof really tricky, I'll circle it in green here, is this distribution step on line 4. If you didn't see that you could do distribution after first doing this commutativity step, you would be really stuck and you wouldn't see how to do this proof. So if you need to, pause this video, take a look at line 1, see what I did on line 3 using that commutativity step right here in order to set up this distribution step. Your ability to do this proof would depend on your ability to see those things. So make sure you pause and understand what I've done there. Okay, let's move on. Next argument. We're given 3 premises. It's not the case that F and A. Line 2 says it's not the case that L or not A. Line 3 says if D, then F or L, and we're just trying to show that D follows. I think there are a couple obvious starting points here. On line 1 and 2, both of those to me look like De Morgan's rule. Line 1 is the negation of a conjunction, and line 2 is the negation of a disjunction. So let's start out by doing De Morgan's rule on both of those premises and see what we get. With line 1, I'm going to get not F or not A by De Morgan's rule. Hopefully that's pretty easy to recognize already. And I'm going to do De Morgan's rule on line 2, which is going to give me not L. And be careful here, right? We're changing the sign from a disjunction to a conjunction, and not A. Not A. That's going to follow from line 2 by De Morgan's rule. Make sure you don't lose track of those negations. It'd be very easy to miss the fact that you need that double negation on line 5. Okay. Now what I see is that, excuse me, I see that I've got a conjunction on line 5, so I could simplify that right off the bat, which I'm going to do. I'm going to get not L on its own line. That's going to follow from line 5 by simplification. I also see that I can get not A on its own line. I just first need to do commutativity to get not A on the left. So let's do that. Let's rewrite line 5 as not A and not L, just switching around the order of that conjunction so we can simplify it and get not A on its own line. That's going to follow from line 5 by commutativity, COM. Okay. We said we did that so we can get not A on its own line. And that's going to follow now from line 7 by simplification. Now here's where you need to think strategically a little bit. You could use double negation to get rid of that double negation and just get A on its own line. In fact, we might need to do that. We don't know yet. But what I notice is that we've got a disjunction on line 4, not F or not A. And now I have the negation of one of those terms, not A on line 8. So this is starting to look like a disjunctive syllogism step. But in order to use disjunctive syllogism, this term that we have the negation of, not A, up here on line 4, has to be on the left side of that disjunction. So I'm going to use commutativity to rewrite line 4 as not A or not F. Okay, that's going to follow from line 4 by commutativity, COM. Now from 8 and 9, I can do a disjunctive syllogism step to get not F on its own line. That's going to follow from 8 and 9 by DS, disjunctive syllogism. I think you can see why, right? Line 9 says either not A or not F. 8 says not A, so obviously the term on the right, not F, would have to be the case. Okay. Line 11. Okay, the next thing I see, and this might be a little tricky, I see that the conclusion, not D, is actually the negation of this, of the antecedent of this conditional on line 1. Now I could get that if I could get the negation of the consequent, not F or not L. In fact, I'll write it down here just as scratch work. If I could get this, then I could get that conclusion by modus tollens. I think that should be pretty easy to see at this point. But the statement I just wrote in the bottom right part of the screen is equivalent to not F and not L by De Morgan's rule. So if I could get not F and not L right here, then I could get the negation of F or L by De Morgan's rule, and then I could get D by modus tollens, and we'd be done. So how can we get not F and not L? Well, I have not F on line 10, and I've got not L on line 6, so I could conjoin those together and get not F and not L by conjunction. That would follow from line 6 and 10 by conjunction, C-O-N-J. Now we're essentially done. We just need to complete these steps that we said we would need to do. So on line 12, by De Morgan's rule, we know we can get the negation of F or L. From line 11, by De Morgan's rule, dm. And finally, we said that once we had the negation of this consequent up here on line 3, the negation of F or L, we knew we could get not D by modus tollens, which is what we're going to do right now. Not T by modus tollens from line, let's see, from line 3 and line 12 by modus tollens. And we're done. We've shown, excuse me, not T. We said we could get not D. There we go. I just put the wrong letter there. And we've shown that the conclusion not D follows. Okay, next proof. We're given three premises. E implies not B, U implies not C. Line 3 tells us it's not the case that not E and not U, and we're trying to show not B, the negation of B and C. All right. I see one fairly obvious starting point. To me, line 3 looks like a De Morgan's rule. We have the negation of a conjunction. So from De Morgan's rule, we can get not E, or make sure you change that conjunction to a disjunction, not U. And that's going to follow now from line 3 by De Morgan's rule, dm. Don't lose track of those negations. You can see how easy it is to lose track of these negations. Okay. I'm starting to see that we're starting to set up a constructive dilemma. I see that on line 1 and 2, E implies something and U implies something. Well, we have not E or not U. So if we can get rid of those double negations, we'll have E or U. So let's do that. Now, because we have two instances of double negations, we have not E and we have not U, we need to do two double negation steps to get rid of both of those double negations. So on line 5, we can get E or not U, eliminating this first batch of double negations right there on line 4. Remember, you can only do one at a time. Don't skip steps. So this would be line 4 by double negation. And we're going to do another double negation step to get rid of these double negations on line 5, E or U. And that's going to follow from line 5 by double negation. Now, the reason we did that is so we can start to set up a constructive dilemma step, right? Now we know that E or U is true. Lines 1 and 2 tell us that E implies something and U implies something. So if we can join lines 1 and 2 together, we'll have statements that match the form for a constructive dilemma. So let's do that. We're going to conjoin lines 1 and 2 together. E implies not B, and U implies not C. And that's going to follow from lines 1 and 2 by conjunction, C-O-N-J. And we said that we were doing that so we can set up a constructive dilemma step. And I think you can see now lines 6 and 7 look like the form for constructive dilemma. We have a disjunction, E or U. Each of those two disjuncts implies something else. Line 7 tells us that E implies not B, and U implies not C. So if either E or U is true, we know that one of the two consequences would have to be true, not B or not C. And that's going to follow from line 6 and 7 by constructive dilemma, which should be review at this point. Okay, so now is a good time to look at the conclusion. The conclusion is the negation of B and C. And by De Morgan's rule, if we could get the negation of B or the negation of C, we could get the conclusion. And we do have that on line 8. So using De Morgan's rule on line 8, we would get the negation of B and C. And that's going to follow from line 8 by De Morgan's rule, and we are done. We've shown that the conclusion follows. Okay. It would be very easy not to see that you need to do this constructive dilemma step, and if you don't see that, you won't be able to complete this proof. So again, if you need to, pause and take a look at how I've applied these intermediate steps, like these double negation steps and this conjunction step, in order to set up that constructive dilemma on line 8. Oh, excuse me, I just noticed this should be line 9, not line 8. I'll fix it right now. There we go, line 9. Okay, so again, if you need to, pause the video, take a look at why I did what I did there. Next proof. We've got three premises, S or I and not J. Line 2 says S implies not R. Line 3 says not J implies not Q. And we're trying to show the negation of R and Q. Okay. Let's see what we can get here. The very first thing I notice is that line 1 seems to match the form for one of the forms for distribution. So I'm going to distribute that S to the other two terms, S or I, and S or not J. That's going to follow from line 1 by distribution. Okay. What I see next, again, this is where you need to pause and take a look and see what's going to be helpful towards getting the conclusion. Line 4 is a conjunction. I could get either of those two conjuncts on its own line. To get the one on the right, S or not J, I'd have to do a commutativity step first. I do want to do that because what I notice is that I have two conditionals up here on line 2 or 3. S implies not R, 3 says not J implies not Q. And if I can get this term on the right on line 4 on its own line, S or not J, I would get something that looks like I could do a constructive dilemma step. So I'm going to do that. I'm going to skip simplifying S or I. I might need to do that. I might not. I don't know yet. But I am going to, first of all, reverse the order of this conjunction on line 4 so I can get S or not J on its own line. So I need to rewrite line 4, S or not J, and S or I. Just reversing the order of that conjunction. So that's from line 4 by commutativity, COM. And I'm doing that so I can simplify and get S or not J on its own line, which is going to follow from line 5 by simplification. Okay. Now we said that together with lines 2 and 3, this is starting to look like a constructive dilemma, but in order to be able to do constructive dilemma, those two conditionals on line 2 and 3 need to be conjoined together on their own line, which I'm going to do right now. So on line 7, we're going to get S implies not R, and, not J implies not Q. The two conditionals from lines 2 and 3 conjoined together. That's going to follow from lines 2 and 3 by conjunction, C-O-N-J. Now I can do a constructive dilemma together with line 6. And again, I'll just go slowly through this. Line 6 says either S is the case or not J is the case. But line 7 tells us that each of those two terms, S or not J, implies something. S implies not R, and not J implies Q. So if one of those two antecedents is true, either S or not J, then one of the two consequents, not R or not Q, would have to be true. Which is what I'm going to get on line 8, not R or not Q. And that's going to follow from lines 6 and 7 by constructive dilemma, CD. And we're very nearly done. Notice now that the conclusion is the negation of R and Q, and we have either not R or not Q. So if we apply De Morgan's rule on line 8, that will give us the negation of R and Q. And that's going to follow from line 8 by De Morgan's rule, and we are done. We've shown that the conclusion follows. This one shouldn't have been too bad. I think the key here is recognizing that you need to do this constructive dilemma step on line 8. If you didn't see that, it would be very difficult to, or impossible to work your way through this proof. Okay, next argument. We're given three premises, A and F and L. A implies something, U or W. F implies something, U or X. And we're trying to show U or W and X. Let's dive in and see if we can figure out how to do this one. The first thing I notice, I'm not sure exactly how we're going to get there yet. I can't tell exactly from looking at this proof right away, but I see that the conclusion matches a form for distribution. By distribution, I would get U or W and U or X. So if I could get that, I could get the conclusion by distribution. So I'm just going to bracket that and leave it up here on the right, knowing that we're going to try to get that. I see how I can get half of it right off the bat. I see that I could simplify line 1 to get A on its own line. Then by modus ponens here with line 2, I could get U or W, and that's half of what we need. Then we would just need to figure out how to get U or X. Well, U or X is already right here in the proof. I just need to get F on its own line. Then by modus ponens, I could get U or X. Then I could conjoin U or W together with U or X, and we'd be done. So this is actually a fairly straightforward proof. Let's dive in and start doing some of these steps we said we could do. We know we can simplify line 1 to get A on its own line. right? That's going to follow from line 1 by simplification. And we said we were doing that so we could do modus ponens together with line 2, right? Line 2 says if A, then that expression in parentheses, U or W. We have A on line 4, so we can get U or W on line 5. That's going to follow from line 2 and line 4 by modus ponens. Next, we said that if we could get F on its own line, then we could get U or X. We just need to figure out how to get F on its own line. Well, line 1 says A is true and F and L is true. But if F and L is true, F has to be true. We just need to figure out how to break this apart. The first thing I see, well, if we could get F and L on the left side of that conjunction, we could simplify it to get F and L on its own line. So I'm going to rewrite line 1 as F and L and A to get that expression in parentheses on the left side of that conjunction. Line 1 by commutativity. Now I can simplify to get F and L on its own line, and that's going to follow from line 6 by simplification. And once I have F and L, I can simplify that to get F on its own line. That's going to follow from line 7 by simplification. Now we said that once we got F, we can use modus ponens together with line 3 to give us U or X, which I'm going to do right now, U or X. And that's going to follow from line 3 and line 8 by our old friend modus ponens. Okay, we're almost done. We said that if we could get U or W, in fact, I'll do it in a different color here so you can see it. If we could get U or W on its own line, and we could get U or X on its own line, we could conjoin those together and then do distribution to get the conclusion. So let's do those steps right now. So line 10, we're going to conjoin U or W, which was on line 5, and U or X, which is on line 9. Let's see, so that was line 5 and line 9 by conjunction. And ultimately we said that then, in fact, I don't need another line, I can do it here. There we go. We said that if we could get that, U or W and U or X, then we could get the conclusion, U or W and X by distribution. So this would be line 10, distribution. And we are done. We've shown the conclusion follows. So that one wasn't too bad, but you might have been stuck if you didn't realize that you could get the conclusion by distribution if you could get this statement, U or W and U or X on its own line. So this is yet another example of how working backwards with rules of replacement or rules of equivalence can help you kind of light the way to how to get to the conclusion. Okay. Next argument. We have P or I and L. Line 2 says, if P or I, then it's not the case that L or C. Line 3 tells us if P and not C, then E and F. And we're trying to get F or D on its own line. So let's see. Before I get started, I'm just going to talk about some of the things I notice. I notice that the conclusion is a disjunction, F or D, but D doesn't appear anywhere in the proof. So we're probably going to use addition at some point in the proof. I also notice that line 1 looks a lot, right here, I'll highlight it, looks a lot like distribution. We have P or I and L, and I could do distribution there, and that would give me P or I and P or L. And that's really handy because that would give us the antecedent of this conditional in line 2. And I think that's all I need to recognize at this point. If we do those steps, I think we'll be off to the races and it will be pretty easy to figure out how to get to the conclusion. So let's add a new line and dive in. We said that we can do distribution on line 1. So let's do that right now. P or I and P or L. Line 1 by distribution. And we said we were doing that so we could get the antecedent of that conditional on line 2. So if we simplify line 4 to get P or I on its own line, in fact, let me cite it here. This follows from line 4 by simplification. That gives us the antecedent for this conditional here in line 2. So we can do modus ponens now. That will give us the negation of L or C. That would follow from line 2 and line 5 by modus ponens. But line 6 looks a lot like a De Morgan's rule step. We have the negation of a disjunction. So let's go ahead and do De Morgan's rule there. That'll give us not L and not C. That follows from line 6 by De Morgan's rule, dm. Now this is pretty handy because we're looking for a way to get F, and F is sort of locked here inside this conditional in line 3. So I know I'm probably going to need this antecedent P and not C to use modus ponens to get E and F, ultimately to get F. Well, we have not C. We just need to figure out how to get not P now. Let's see what we can do. The thing I notice is that on line 4, we have P or I and P or L. We've already simplified to get P or I. Let's simplify to get P or L on its own line and see if that's helpful. I think it will be. Okay, line 8. First of all, we need to reverse the order of that conjunction in line 4 to get P or L on the left. So P or L and P or I. Okay, that's going to follow now from line 4 by commutativity, COM. Excuse me. So we'll simplify to get P or L on its own line. Line 8 by simplification. Now we know L is false. Line 7 says L is false and C is false. We just need to simplify to get not L on its own line. So not L, that's going to follow now from line 7 by simplification. Okay, lines 9 and 10 are starting to look like a disjunctive syllogism. We have P or L, but we know L is false. But in order to be able to use disjunctive syllogism, we need to reverse the order of that disjunction so L is on the left. So line 11, L or P, and that's going to follow now from line 9 by commutativity. And we're doing that so we can do disjunctive syllogism, which we're going to do right now. Line 11 says L or P. Line 10 says L is false. So we know P has to be true. And that's going to follow now from line 10 and 11 by disjunctive syllogism. Okay, just to remind you of where we were headed, a few moments ago, we said that if we could get P and not C on their own lines, then we could get E and F, which means F would be true, and then we could use addition to get F or D. We're almost there. We need to get P and not C on its own line. Well, we have not C. It's just locked up here in the conjunction in line 7. So if we could simplify not C out, then we could get not C, connect it together with P using conjunction, and we'd be off to the races. But in order to be able to get not C on its own line, we first need to reverse the order of that conjunction on line 7, so not C is on the left. So not C and not L. That's going to follow now from line 7 by commutativity. And we're doing that so we can simplify to get not C on its own line, which is what we said a moment ago. So line 13 by simplification. Okay. Remember where we're going here. We said that if we could get P and not C, then we could get E and F. We know we need F, so we got to do those steps. So line 15, we're going to get P and not C by conjunction from lines 12 and 14. C-O-N-J. I think you can see these proofs are getting a little longer, so make sure you're getting plenty of practice working through these longer proofs in your homework exercises. Okay, we said from there we could do modus ponens, right? Line 3 says if P and not C, then we get E and F. We already have P and not C now on line 15, so we can get E and F. That's going to follow from line 3 and line 15 by modus ponens. Now we said we needed to get f on its own, and if we could do that, we could use addition to get f or d and reach the conclusion, and we would be done. So we need f on its own line. To get that, we need to reverse the order of that conjunction in line 16, so f is on the left, f and e. And that's going to follow from line 16 by commutativity, C-O-M. That would give us f on its own line, which is what we said we would do. Line 17 by simplification. And now we're almost done, very last step. We said if we, I'll do it in a different color here so you can see it. We said that if we could get f on its own line, we could then use addition to get f or d. We have f on its own line on line 18, so line 19 will just be f or d. And that would follow now from line 18 by addition. And we are done. We've shown f or d follows. Okay. A pretty long proof, but it wasn't too bad. There were a couple of key steps to notice, and a lot of mechanical steps, a lot of commutativity steps, things like that to set up the important steps. If you need to go slowly through this proof, back up the video, pause for every step, make sure you can see what I'm doing to get the overall conclusion here. Don't just blaze through if you don't see why I'm doing every step. Okay. Next proof. We've got a conditional in line 1. If not M or E, then S implies U. Line 2 says, if either not M or E, then U implies H. Line 3 tells us it's not the case that M or Q, and we're trying to get S implies H. I only see one really obvious starting point here, and that is what I'm going to do first. Hopefully you see by now that line 3 is a De Morgan's rule step. You can see that it's the negation of a disjunction, which would give you not M and not Q. Okay, and that would follow from line 3 by De Morgan's rule. It's the only obvious starting point that I see. The next thing I notice, I'm looking at the conclusion. I see the conclusion as S implies H. And those terms, S and H, are kind of locked up here. In fact, I'll circle it there, only to delete the circle. I see that they're kind of locked up here in these conditionals. S implies U, but U implies H. So if I could get those two terms on their own, S implies U and U implies H, I could use hypothetical syllogism to give me S implies H. The question becomes, how then can I get those two consequences, S implies U and U implies H, on their own? And the obvious answer is that, well, I need the antecedents. I need not M or E, the antecedent to line 1, and I need not Q or E, the antecedent to line 2. Now I have not M and I have not Q on line 4. Line 4 says not M is the case and not Q is the case. If I could get those on their own line, not M and not Q, I could use addition to get not M or E and not Q or E, adding E in as addition onto not M and onto not Q. And then we'd be off to the races and the proof will fall out pretty easily from there. So let's do that. If we know we need to simplify those terms on line 4, let's simplify both not M and not Q. In order to get not Q on its own, we're going to need to reverse the order of that conjunction on line 4, which I'm going to do right now. Not Q and not M. So this would be line 4 by commutativity. And now I can simplify and get not M on its own line from line 4. By simplification. And on line 7, I could get not Q, and that would follow from line 5 by simplification. Okay, just to remind us where we are, we said that if we could get not M on its own line and not Q on its own line, we could use addition to get the antecedents to these conditionals in lines 1 and 2 by adding E onto each of those terms with a wedge using the addition step. So I'm going to do both of those now. I'm going to do them back to back so you can see why I'm doing this. From line 6, I'm going to get not M or E, using the addition rule to add this E onto not M with a wedge. So that would be from line 6 by addition. And I'm going to do the same thing with line 7. from line 7, I'm going to get not Q or E. And that's going to follow from line 7 by addition. Now we have our antecedents to those two conditionals in lines 1 and 2. So I know I'm going to do two modus ponens steps next, which I'm going to do right here in lines 10 and 11. Modus ponens from line 1 and 8 will give us S implies U. Line 1, line 8 by modus ponens. You need to pause and see how I'm doing that. And we're going to do another modus ponens step with line 2 and line 9, and that will give us U implies H. So this is line 2 and 9, which I lovingly call our old friend modus ponens. And we're almost done. Remember, we said that if we could get S implies U on its own line and U implies H on its own line, then we could do a hypothetical syllogism step to get S implies H. And I think you can see that now from line 10 and 11. Line 11 says U implies H. Line 10 says S implies U. Line 11 says that U in turn implies H. So on line 12, we can get S implies H by hypothetical syllogism from lines 10 and 11, HS. And we're done. That one took quite a few fewer lines than the previous proof. But the key here was recognizing that you needed these consequents. In order to get that, you need these antecedents. And in order to get that, you had to do these two addition steps right here on lines 8 and 9. If you didn't see that, you really would be stuck and you wouldn't be able to plow through this proof. So again, use the equivalence rules, or what the book calls the rules of replacement, to work backwards. And hopefully that will light the way to what you need to do in order to complete the proof correctly. Okay. Next example. We have three premises. We're given not Q implies C and B. We're given not T implies B and H. We're given the negation of Q and T, and we're trying to show that B follows from that. Let's see what we can do. I think there's an obvious first starting point, which is to use De Morgan's rule with line 3, and that will give us not Q or not T. That would follow now from line, that would follow from line 3 by De Morgan's rule. Okay, the next thing I noticed, this is going to look a little scary because we're going to have to invoke some brackets here to work our way through. But line 4 says not Q is the case or not T is the case. And lines 1 and 2 tell us that each of those two terms implies something. 1 says not Q implies something, 2 says not T implies something. And this is starting to look a lot like a constructive dilemma. We just need to set it up as a constructive dilemma. And remember, when you have a constructive dilemma like this, those two conditionals that you see on line 1 and 2, those need to be conjoined together with a dot. So I'm going to introduce some brackets here, and I'm going to say not Q implies C and B, and another set of brackets, not T implies B and H. Kind of a long expression. That's going to follow from lines 1 and 2 by conjunction, C-O-N-J. And I'm doing that so I can do constructive dilemma. I think you can see this now. Even though line 5 is pretty scary looking, take a look at what you've got. Line 4 says either not Q is the case or not T is the case. And line 5 now says each of those two terms implies something. Not Q implies C and B, and not T over here on the right implies B and H. So by constructive dilemma, if one of those two antecedents, not Q or not T is the case, one of those two consequents, C and B or B and H, would have to be the case, which is what I'm going to get on line 6. So we get C and B or B and H. And that's going to follow now from line 4 and 5 by constructive dilemma. Even though this is a little scary looking, this should still be a review. If you need to, pause and see exactly how I've gotten line 6 from line 4 and 5. Okay. What I see next is that line 6 is starting to look an awful lot like a distribution step. But in order to make it match the form for distribution exactly, I'm going to need to do commutativity right here on the antecedent, or not the antecedent, on the left and disjunct of this disjunction on line 6. So what I'm going to do, I'm going to rewrite this as B and C, just switching around the order of the conjunction on the left side of line 6, and leaving the rest of the statement alone, or B and H. And that's going to follow from line 6 by commutativity. Again, what's unique about these rules of replacement is that you can apply them to a part of a line, which I've done right here. I've just applied commutativity to the part of line 6 that you see that I've highlighted there in pink. Okay. Now we can do distribution on line 7. That's going to give me B and C or H. Right, and if you apply distribution to line 8 now, kind of in reverse, you get B and C or B and H, which is what we have on line 7. I think that makes the distribution step a little easier to see. So this is going to follow from line 7 by distribution. And look how easy this is. Once you get B and C or H, all we're trying to get is B. And line 8 is a conjunction, so we can just simplify to get B on its own line, and we are done. That's going to follow from line 8 by simplification. This was really not a hard proof. The only thing that you absolutely had to recognize was that you had to do this constructive dilemma step. And in order to do that constructive dilemma step, you had to see that you needed to conjoin those two conditionals together on lines 1 and 2 to get that very long statement on line 5. If you didn't see that, you really would be stuck and you wouldn't be able to get to the conclusion. Okay, let's do one more example, and then I will give you the rest of your week back, get you busy working on your exercises for the week. Okay, so in this example, we are given two premises, M and N or O and P. We're given N or O implies not P, and we're just trying to prove that N follows. Okay, so this is a fairly tricky proof, and it hinges on your ability to see this. If you notice on line 1, we've got a disjunction, M and N or O and P. We can actually do distribution on this, distributing this entire term on the left to both of these two terms on the right. So if we do that, we're going to get something like this. We're going to get M and N or O in brackets, and in another set of brackets, M and N or P. Okay, that is a pretty scary looking step, and it's one that if you really would have to stare at this proof for a while before you recognize that that's what you needed to do. Let's write it down here. This is going to be line 1 by distribution. I'm going to write small because this is going to be a fairly long proof, I believe. Okay, on line 4, we can actually simplify this now, right? Line 3 is just a conjunction, that expression on in the brackets on the left and the expression in the brackets on the right. Let's go ahead and simplify that. We're on its own line now. We're going to get M and N or O. And that's going to follow from line 3 by simplification. Okay, this is pretty handy because this is starting to look like another distribution step. But we need to get that O on the left side. So let's do that. O or M and N. Just reversing the order of that disjunction on line 4. Line 4 by commutativity. Just reversing the order. So we can do distribution. And if we do distribution again on line 5, distributing this O to both of these terms, M and N, we're going to get O or M and O or N. And that's going to follow now from line 5 by distribution. Okay. Well, once we have O or M and O or N on their own lines, we can simplify each of these two terms out. In fact, let's do that. We can get O or M on its own line. That's going to follow from line 6 by simplification. Oops, excuse me, this should be line 7, not line 6. Fix that real quick for you. There we go. And we can get O or N on its own line, but we first have to reverse the order of that conjunction on line 6 using commutativity. So I'm going to do that right now. O or N and O or M. And that's going to follow from line 6 by commutativity. Okay. We did that so we can get O or N on its own line now. from line 8 by simplification. Now we said back here on line 2 is just a conditional. If in or O, then not P. Well, we almost have in or O. We have O or N. We just need to do commutativity to make it match the form of that antecedent in line 2, N or O. Line 9 by commutativity, COM. I'm going to draw a dividing line here. We're going to keep going. It's going to be a fairly long proof. Once we have in or O, we know that not P would have to be the case, right? That would follow now from line 2 and line 10 by modus ponens. Okay, notice now that we simplified line 3 and got the term on the left, that term in brackets on the left, and we haven't done that with the right though. The expression on the right here, I'll underline it in green so you can see it. This expression right here on the right says M and N or not, or P. But we know P is false here on line 11. So if we could get that expression on its own, that expression in brackets, M and N or P, we could use disjunctive syllogism to get M and N, and we could just simplify and get N, and we'd be done with a few intermediate steps. So let's go ahead and do that. In order to simplify that term out of line 3, we need to rewrite all of line 3 so that that term in brackets that's now on the right on line 3 is actually on the left. So we're going to rewrite this. I'm going to kind of squeeze this in here. That expression in brackets on the right is now on the left with a dot. I'm going to keep going just on the next line, but I think you'll see what I'm doing here. I'll indent it just a little bit. Or M and N or O. And this would follow now. I'll do it all right here. This is just one line from line 3 by commutativity, COM. Just reversing the order of that long conjunction in line 3. Okay. Now we're going to simplify that out now, so the term on the left right here is on its own line, M and N or P. And that's going to follow from line 12 by simplification. Okay, we said we were doing that so we can do a disjunctive syllogism step with line 11, but in order to do that, we need P to be on the left side of this disjunction in line 13. So I'm going to use commutativity to rewrite this as P or M and N. That's going to follow from line 13 by commutativity, COM. Now I can do disjunctive syllogism. I think this is pretty clear. We have P or M and N. P is false on line 11, so we know M and N has to be true. That's going to follow from line 11 and line 14 by disjunctive syllogism, DS. Now we're just trying to get N on its own line. We have M and N, so obviously N is true. N just needs to be on the left side of that conjunction. So I'm going to rewrite line 15 as N and M. That's going to follow from line 15 by commutativity. And finally, very last step, we can get N on its own line, and that follows from line 16 by simplification. Okay, so that's the last proof I have for you guys. Just as a quick reminder, we'll scroll all the way back up here. There are 5 new rules. Double negation lets you introduce or remove a double negation. You've got commutativity that lets you switch around the order of a disjunction or a conjunction. You've got De Morgan's rule that lets you distribute the negation to both terms of a conjunction or a disjunction as long as you change the sign from a wedge to a dot or vice versa. Associativity lets you switch around the order of a string of disjunctions or a string of conjunctions. And distribution lets you take a term like this, P and Q or R, distribute the outside term to the 2 terms inside the parentheses, as you see shown here. So P and Q or R would be equivalent to P and Q or P and R or vice versa. And P or Q and R would be equivalent to P or Q and P or R as shown here. Make sure you get plenty of practice using these rules for your homework exercises. Again, all of the challenge of doing proofs is in a couple of things. A, seeing what steps are going to be necessary to get to the conclusion and what intermediate steps you need to do in order to be able to apply those key steps correctly. It can be very helpful to use equivalence rules to work backwards from the conclusion or work backwards from something you know you need. Hopefully that will light the way. But some of these proofs, like the last one we did, which I'm going to pull back on the screen right now, some of these are really, really tricky. Like you really would be stuck if you didn't see that you could do distribution like this on line 1, distributing this term on the left to both of these two terms on the right in premise 1. If you didn't see that, you would be really stuck and you wouldn't be able to work your way through this proof. And sometimes, frustratingly, you'll have to sit and stare and try various things, try a path, see that it doesn't work, back up and see that you missed something that you didn't see. You know, you could stare at this proof for 10 minutes and not see that you could apply distribution in this way on line 3, and you'd be stuck. So get as much practice as you can on your homework exercises. Do all the ones I've assigned. Watch this video. Make sure you understand every step in this video. Do the sample proofs that are given inside the textbook chapter itself and get lots of practice. And next week, we're going to get another batch of replacement rules or equivalence rules, and we're going to keep building our system of proof rules from here. Definitely let me know if you have any questions. I'm very easy to get a hold of. Get a hold of me by phone or by email. We can always jump in a Zoom meeting if you need help working your way through a proof, if you're stuck anywhere, if you don't see how to do something, if anything isn't clear. I'm always happy to help. Other than that, hope you guys have a great week, and I'll look forward to seeing you in the next video a week from now. Take care.